Welcome. This is a dive into Solidity programming with MacroDAO. We are going to do this course in two stages. First, we are going to do a comprehensive dive into the Solidity programming language. And second, we are going to put our new skills to work, develop a real smart contract together, deploy it to a test network, write a test suite for it, the whole shebang. Quick PSAs before starting the course. If you have not completed part 1, 2, and 3.1 of Teach Yourself Web 3, aka Macro Engineering Fellowship Pre-Course, please go do so before continuing any further. The link can be found in our GitHub repository in the README right here, in our GitHub repository in the README right here, which you'll download in just a second. So back to the course. Let's talk about what this course is. It's a comprehensive course on the Solidity programming language. You will learn the ins and outs of the syntax, as well as how to write tests and deploy smart contracts to EVM-compatible blockchains. This course will be a great stepping stone for you on your journey into Web3. What this course is not, this course will not make you a smart contract developer overnight. It will not deeply touch on smart contract security, which is a major importance to the discipline of smart contract programming. Keep in mind that there will be a lot more to learn after this course on your journey, and we will help guide you towards those things. Our class's GitHub repository can be found here at github.com/0xmacros/dive into Solidity Udemy course. So without further ado, let's get started. Welcome to lesson 1 in Master the Solidity Programming Language. First things first, we're going to look at our development environment, which in this course we'll be using Hardhat. We're going to take a quick look at their docs to get started. Before we get started with that, I also want to give a quick shout out to Foundry, which is gaining a lot of popularity amongst developers. It is probably the best alternative to Hardhat. So if you feel like using Foundry, we really encourage you to use it later in your own endeavors. So quick overview. Hardhat is a development environment to compile, deploy, test, and debug your Ethereum software. It helps manage and automate the recurring tasks that are inherent to the process of building smart contracts and dApps, as well as easily introducing more functionality around this workflow. This means compiling, running, and testing smart contracts at the very core. Hardhat comes built in with Hardhat Network, a local Ethereum network designed for development. Its functionality focuses around Solidity debugging, stack traces, console logs, and explicit error messages when transactions fail. So let's go over how to install. First, I'll just open up a terminal window. I've made a new directory called hardhat test, and we simply type npx hardhat. By the way, this assumes that you have Node installed on your local machine. So here, Hardhat gives us a few different options. We'll start with a basic sample project. And I'm just going to hit yes to the following things, but feel free to read them. Just some nice to haves, like adding a .git ignore file and adding a few ethers/hardhat dependencies like Ethereum waffle, chai, hardhat ethers, hardhat waffle, etc. These things just make it easier to navigate the hardhat environment, and we'll be using them in our testing suite, in our contracts, etc. So now that npx hardhat is done running, let's just take a look at it in VS Code real quick. You can see here, they gave us a sample contract. The node modules folder has all of the dependencies inside of it. In the scripts, we have a sample script. Tests, we have a sample test. Hardhat config.js. This is where we configure all the settings for the Hardhat environment. Our README, obviously, we can edit this later, but for now, it gives you a good list of some common scripts that you might be running in the Hardhat environment. So overall, gives you this nice clean directory to write your contracts, tests, and helper scripts. That concludes our lesson on Hardhat. Another cool tool to have in your toolbox as a Solidity developer is Solidity Shell. It's basically a CLI that lets you evaluate Solidity on the fly. We won't be explicitly using it in this course, but if you ever need to evaluate what a line of code is doing, I highly encourage you to use it. Let's look at their GitHub page quickly. You can find Solidity Shell, how to install it here, npm install-g Solidity Shell. Okay, so to use it, we'll just type in Solidity Shell. So we can just start writing some Solidity code. Let's start here. Uint 256, A is equal to 10. Uint 256b is equal to 12. So if we did a plus b, we get 22. We do a minus b, we'll get an error because there is an underflow. So that's Solidity Shell. I highly encourage you to use it. It's a great tool. So you already know what a smart contract is, but let's take a look at the layout of a smart contract in Solidity. So there are three main parts to the layout. The first part is the SPDX license. This is not required, but the Solidity compiler will throw a warning if you don't include this when you compile your contracts. So what an SPDX license is a machine readable license identifier. This allows you to put various license to determine how your code can be used. And just be sure to include these before deploying your code to an actual blockchain, because once you deploy it, as we know, smart contracts are immutable, so you won't be able to change this. Next, we have the pragma keyword, which indicates the version of the compiler to be used. And then finally, we have the contract keyword. So let us look at this in code. You can see at the top, I have commented out my SPDX license. In this case, I'm using the MIT license, but you can use whichever license you would like. Next, we have the pragma keyword. This determines the version of the Solidity compiler that we will compile the following contract with. You can see this keyword pragma, then Solidity, and then finally we have the version. This caret means that we will not use any version less than 0.8.13, but we also won't use any version greater than 0.9.0. So any releases in 0.8 after 0.8.13 will be valid to compile this contract with. This is also a valid pragma statement. Here we are saying we won't use any version of the Solidity compiler that is less than 0.5.0 or greater than 0.9.0. In our case, let's just stick to a more modern version of the compiler, 0.8.13. Next, we have the contract keyword. Here we are defining a contract and we are giving it a name. We name our contracts with capital letters, and following that, we use camel case. So the contract code lives inside of these curly brackets. There is no contract code because we are getting there in the following lessons. See you in the next one. Hi, in this lesson, we're going to go over some of the basic syntax rules of Solidity, which is influenced by JavaScript and C++. Solidity is a C-level language, which basically means it allows us to go as low level as we want, managing the memory, writing opcodes and assembly, etc. Sol C stands for the Solidity compiler, which you'll be interacting with quite a bit. Solidity is case sensitive, like all other programming languages, as far as I know. Every statement in Solidity must end with a semicolon. Curly braces are used to scope blocks of code. 2 forward slashes represents a single line comment. / is a multi-line comment. 3 slashes represents a natspec comment, and this last represents a multi-line natspec comment. Natspec is used for inline code documentation. You can read more about the Solidity natspec here at this link. It is also in our GitHub repository. And finally, most logic statements are available, such as if, else, while, for, break, continue, return, and the ternary operator. Now let's hop into some code. You can see just about all of the rules we've talked about are in this file, even though it is somewhat short. You're familiar with lines 1 through 3, the SPDX license, and the pragma Solidity statement. Lines 5 through 10 show a multi-line natspec comment. On line 14, you can see we've defined a uint 256 public variable called price. On line 16, we have a single line natspec comment, which describes the function on lines 17 through 19. This function, setPrice, takes in a uint 256 variable called newPrice. And what this function setPrice does is sets our price variable equal to the new price. That is it for the basics of the Solidity programming language syntax. Welcome to our lesson on state and local variables. As we know, Solidity is a statically typed language, which means that the type of each variable needs to be specified when declaring the variable. We have two types of variables, state and local variables. State variables are declared at the contract level. They are permanently stored in the contract storage. They can be set as constants. They are typically initialized at declaration using a constructor or after contract deployment by calling setter functions. However, they are more expensive to use than local variables. Local variables are declared inside of functions. They have access to the call data, memory, and storage keywords for non-primitive variables. They can be cheaper to read and write than storage variables, but that does depend on the context. But most of the time, they are much cheaper. Let's take a look at some code. You can see in our contract that we declare a new variable that is of type uint256 called price. We are setting it equal to 100. In Solidity, variables also have a visibility. In this case, it is public. We will talk more about visibilities later in the course. State variables are declared at the contract level. Saving state variables is not free. You have to pay gas. There is no specific cost for storage, only gas for execution. For dynamic storage, the store opcode stores a 256-bit word. It costs 20,000 gas when the value is set from 0 to non-zero, 5,000 gas when the value is set from non-zero to non-zero, and the EVM provides a refund of 15,000 gas when the value is set from non-zero back to 0. To save a state variable as constant, simply use the constant keyword. Constants are named in all caps as per best practices. If you do not provide a value to a constant variable, you will get a compilation error. In Solidity, the concept of null values or undefined does not exist. When you declare new variables, they always have a default value based on their type. When declaring a local variable inside of a function, that variable is kept on the stack, not on storage, so they do not save their value across function calls. You can see here in our function setPrice, we take in a parameter called _price. This _price variable is saved in memory and is not accessible anywhere else in our contract. Here we are setting our price variable in storage to the _price. So we are saving the _price variable from memory into our price variable, which lives in storage. This will trigger an store opcode, so we will pay the price to store this memory variable. This will cost 5,000 units of gas because we are updating a non-zero variable to another non-zero variable, assuming _price is not 0. These are the two types of places that we can store variables. Hi, welcome to State and Local Variables Part 2. Here are the default values for various types in Solidity. You can download this slide in the resources or check out the Solidity language docs to go into more depth of this topic. In this lecture, we will be talking about functions. A function is an executable unit of code inside of a contract. Solidity is an object-oriented programming language, which means we will be using setter and getter methods. Functions in Solidity require a visibility specifier, just like variables. Functions and variables combine to create a contract's interface. Let's jump into code so we can touch on the syntax of writing functions. In our contract, you can notice how we have two variables in state, one price and the other location. Location is a constant, which means that we cannot change its value after it's instantiated. Given that location is a public variable, a getter function is automatically created. The same can be said about price. Given that it's public, there is a getter method which returns the value of the variable. In price, if we called the getter function, it would return 100. And for location, it would return the string outer. We have one function in our contract, and that is called setPrice. This is our setter function. Notice how we pass in a variable with the same type as our price variable, and we update the variable of price in storage to the parameter in memory that we passed in. To create a function, use the function keyword, followed by the name of the function, and then a pair of parentheses. Inside of the parentheses, we will put the parameters of the function, if it has any. If the function has more than one parameter, we can separate them with commas. You can see that we named our parameter _price as to differentiate it from our state variable with the same name, minus the underscore. Price is stored in storage, _price is stored in memory. Each function must have a visibility specifier after the parameter list. Our function is public, which means that it is part of the contract interface and can be called internally by this contract or externally by other contracts. Other visibility specifiers are private, internal, and external. We will go in depth on these in a later section. If the function is read-only, it will get the modifier view or pure. But in this case, our function is not read-only, therefore we will not be using view or pure modifiers. If the function returns a value, it should be indicated using the returns keyword, and the type of return value should be indicated inside of the parentheses following the return keyword. Let's take a look at this now. This is how you would have a return value in a function. You can also return more than one value in a tuple, like so. That's our lesson for functions, getters, and setters. The constructor is a special function that executes only once when the contract is deployed. There is only one, and it is optional. One of the main use cases is to initialize state variables when the contract is deployed by an externally owned account or another contract. When deploying a contract that has a constructor with parameters, these values must be supplied in order to successfully deploy the contract. Let's look at how we can write constructor functions in our smart contracts. The constructor function is created by using the constructor keyword. There is only one constructor per contract, and it is optional. We use parentheses with any parameters that we may pass into the constructor, just like a function, and then the body of the constructor lives within the curly brackets. The visibility of the constructor, which is normally public, should be ignored with Solidity versions greater than 0.7.0. It is very common for contracts to have an owner that is instantiated in the constructor. Many times we want to set the owner to be the deployer of the contract. We can use the message.sender keyword to get the address of the account that initiated this transaction. In this case, the constructor runs on contract deployment. So message.sender would be the address of the contract deployer. We have set a state variable named owner, which is public and immutable. The immutable keyword allows us to define a state variable's value within our constructor function, but after we assign it value, it's essentially constant. It can't be changed later on. We would not be able to create a setter function called setOwner if the owner variable is immutable. Immutable variables and constant variables are both much cheaper than normal state variables. That's because their data is stored directly in the bytecode of the contract. That was our lesson on constructor functions. Hi, and welcome to our lesson on Boolean and integer types. Once again, Solidity is a statically typed programming language, which means we must specify the variable type at declaration. First, we'll go over Boolean values. As we all know, Boolean values can either be true or false. They are initialized as false by default. There are two types of integers, signed and unsigned integers. The difference is that unsigned integers are always positive, where int values can be both negative and positive numbers. They range from integer 8 and uinteger 8 all the way up to 256 and uinteger 256. This translates 2 to the 8th power and 2 to the 256th power. Simply writing int will initialize it int 256. Same with writing uint will initialize a uint 256 variable by default. Both uint and int types are initialized with 0 by default. Let's take a look at some code. This contract has 3 variables. On line 8, we have a bool public sold. Sold will be initialized with false by default. Then we have a uint public price and an int public location. Integers will always be default 0. Now you know how to instantiate Boolean and integer types in Solidity. Hi, and welcome to our lesson, Safe Math, Overflows, and Underflows. If you've written code in low-level languages before, you should be familiar with this concept. Overflow and underflow errors occur when the maximum number in an integer variable is exceeded, which causes the number to wrap around the range of valid integers. In an overflow, this would turn from the maximum possible value to 0, and an underflow from 0 to the maximum. Ethereum hosts a wide variety of financial applications, so it's easy to understand how an overflow or underflow could have disastrous results. In April of 2018, 2 types of vulnerabilities were found. batch overflow, and proxy overflow. These were found in some ERC20 tokens on Ethereum. The result was that billions of dollars of tokens were created out of thin air. I've attached an article to a post-mortem which goes in depth on how this attack worked. In a result to this attack, centralized exchanges halted all trading of ERC20 tokens, which caused a lot of fear and doubt in the community. Let's take a look at how underflow and overflow works in Solidity. On line 8, we've initialized a uint8 public variable named price. We've set its value to 255, which happens to be the max value that we can store in a uinteger 8. In our function f1, you can see that we perform an unchecked arithmetic where we add 1 to the price. This will cause an overflow, and the result of the first call to f1 will be 0. We have a second function called f2 where we do not perform unchecked arithmetic. This function will revert if price is equal to 255. This is because in Solidity, after version 0.8, underflow and overflow checks are built into the language on all arithmetic. If you want to use the original behavior of the language pre-version 0.8, you can add the unchecked flag and put all of your arithmetic within this scope. Before version 0.8, it was very common to use a library by OpenZeppelin called SafeMath. SafeMath wraps each calculation in a series of checks, such as a plus b equals c, c is greater than a and b, and so on. We no longer need to use SafeMath after version 0.8 because this is built into the language. It does add extra gas costs to each operation, so if you did want to save gas and there's no way that you could overflow or underflow with a given operation, you can put the unchecked flag, but be very careful when doing so. That was a lesson on SafeMath, overflow, and underflow. Let's look at another Solidity data type, arrays. There are two types of arrays in Solidity, fixed and dynamic. A fixed size array has a fixed number of elements predetermined when you write the contract, and this length cannot grow or shrink during runtime. On the other hand, a dynamically sized array does not have a fixed number of elements and can grow and shrink at runtime. As in other programming languages, array indexing starts at 0. Let's look at fixed size arrays first. Array elements can be of any type, including int, address, mapping, struct. The only restriction is that all elements of the array must be of the same type. If you try to access a variable at an index that is equal to or greater than the length of the array, you will get an out-of-bounds error. Let's talk about length. Length is a member of both fixed and dynamically sized arrays. The number of elements in the array starting from 1. An empty array will have a length of 0. Dynamically sized arrays have two other members, called push and pop. Push will add a new element to the end of the array. It will also add 1 to the length member. Pop will remove the last element in the array and subtract 1 from the lengths. Let's look at a special type of the array, bytes. You can see here that we've defined 3 variables, b1, which is type bytes1, b2, which is type bytes2, b3, which is type bytes3, and so on. You can define up to type bytes 32. A byte consists of 8 bits, and a hex digit occupies 4 bits. By default, bytes have a value of 0. So you can see our variable b1 will be equal to 0x00, b2 0x0000, and so on. This is because bytes are formatted in hexadecimal, and so since each byte is 8 bits and each hexadecimal character is 4 bits, we can have 2 zeros here. Let's look at a function that will change the elements of an array of type bytes. On line 27, we have setBytesArray, which is a public function. You can see we go line by line, setting bytes 1, bytes 2, and bytes 3 to new values. On line 29, we are setting the variable b1, which is of type bytes1, to the string a. This will result in 0x61. This is because the characters were encoded in UTF-8, which is a superset of ASCII, and they are shown as hexadecimal values. 61 is the hexadecimal code for the letter A. On line 31, we set b2 to the string AB. You can see that this would result into 0x6162. 61 is the code for A, and 62 is the code for B, and so on. You can see how this manifests in bytes 3 is equal to ABC. Finally, on line 35, we set bytes 3 equal to Z. The character Z only occupies 8 bits, but in our type bytes 3, we have space for 24 bits. So we pad the remaining bits with zeros. You can see here bytes 3 equal to string z is equal to 0x7a0000. Notice that we cannot access bytes 3 at 0 like we can with a normal array. This will not compile since you cannot edit single bytes in a bytes array. You can only overwrite the entire bytes array. Also notice that the keyword byte is an alias for bytes 1 in Solidity prior to version 0.8.0. You might run into this in legacy code. Now let's look at two examples of fixed arrays. On line 16, we've declared a variable called 3 zeros, and we have given it the type of an array of uints, and we have specified that there will be 3 elements in this array. Because we have not set the array's values, it will be initialized as this array of 3 zeros. Below it, we have defined another fixed array with type uint. The length of this array is also 3. We have defined each element inside of the array as 2, 3, and 4. Here we have defined a function called setElement, which takes in 2 arguments, an index and a value, both of type uint. You can see on line 20 how we use these parameters to change the value at a specific index in the numbers array. Below it, we have a function called getLength, which returns the length of the numbers array. In this case, it will always be 3. That is all for our lesson on fixed sized arrays. Hi, we're going to have a lesson on dynamically sized arrays now. I just wanted to add, as an addendum to the last lesson, that dynamically sized arrays do have a method pop, which removes the last element in the array and subtracts 1 from the length member. I realized I didn't have pop in the last slide, so just thought you guys should know that. Let's look at some code examples. So dynamic arrays are arrays that do not have a predetermined size at the time of declaration. Their size is determined at runtime. Dynamic arrays can hold any type of element as long as they are all of the same type. Dynamic arrays have 3 members, length, push, and pop, which we've already gone over. Keep in mind that push has a constant gas cost, while pop has a cost that depends on the size of the array. Let's look at an instance of each member of dynamic arrays. So on line 7, we declare a dynamic array of uints called numbers. Our function getLength returns the length member. Our function push will push a uint item to the end of the array. And our function popElement will pop a number off of the end of the array. Notice that we also have this way of deleting indexes. Let's say you wanted to remove an element from the array, but that element was not necessarily the last element in the array. So we cannot use pop for this scenario. We can use the keyword delete and then grab the element that we want to delete by passing in its index to the numbers array. However, this acts differently from pop. It will not subtract 1 from the length. It will just reset the element to the default value. In this case, for uint, it is 0. Besides storage arrays, which we have just looked at, there's another kind of array called memory arrays. The memory keyword will create a new array in memory. Memory arrays cannot be resized, so the push and pop methods are not available. You either need to calculate the size in advance or copy every element from an existing array. You can see us instantiating a new memory array on line 31 and subsequently accessing each of its elements below. Notice that we are using the pure keyword in our memory array function. This is because we do not read or write anything from the blockchain. This code runs completely independently. If we were reading an array, we would use the view keyword. However, we are not, so we will use pure. Just to recap, pure does not read or write anything to the blockchain, while view only reads from the blockchain and does not write. Both pure and view functions are free to call from externally owned accounts. But when calling in the context of another function call, you do pay the gas. That is all for our lesson on dynamic arrays. Bytes and strings are another data type in Solidity. Both bytes and string types are a special kind of dynamic array. String is equal to bytes, but it does not allow length or index access. As a rule of thumb, use bytes for arbitrary length raw byte data, and string for arbitrary length string UTF-8 encoded data. In our contract, we have 2 state variables, B1 and S1. We've both set them equal to the same string, ABC. However, our B1 variable, which is type bytes, will indeed store the hexadecimal value of this string, 0x616263. As we talked about before, these are the ASCII hexadecimal characters for these letters. On the other hand, our string, S1, will just store this string, which is UTF-8 encoded as ABC. Because bytes are a special kind of dynamic array, in our addElement function, We can call b1.push and add a new element to our bytes array. The result would look like this. However, strings do not have access to the normal dynamic array methods, so calling string1.push would not work. This is the same for accessing elements at a specific index. We cannot access specific indexes of strings. However, with bytes, we can do so. The same goes for length. It is also important to remember that fixed-sized arrays use less gas than dynamic arrays. That concludes our lesson on bytes and strings. Solidity mappings are similar to a Python dictionary, a Go map, or a Java hash map. Mappings hold key-value pairs. All keys must have the same type, and all values must also have the same type. The two can be of different values, of course. So you could have a mapping from address to uint, or uint to boolean, and so on. The keys of a mapping cannot be of types mapping, dynamic array, enum, or struct, but the values can be of any type. Mappings can only have a data location of storage. This means we cannot declare mappings in memory. The advantage of mappings are that they have constant time lookup, no matter the size. To get a value from the mapping, we provide a key which gets passed through a hashing function that outputs a predetermined index that returns the corresponding value from the mapping. Mappings, unlike arrays, are not iterable. If you instantiate a public mapping, a getter function is automatically created. This getter function will take an argument, which is a key, and return the value according to that key. If you search for an unexisting key in the mapping, it will return the default value for the type of the mapping value. So, if the mapping value is Boolean, this will return false. If it is a uint, it will return 0, and so on. Here we have an auction contract, where users will bid an ETH value for a product or service, and the highest bidder will win. Our mapping will have keys of type address and values of type uint. The value will be the amount of whey sent to the contract by each address. There are multiple ways for a smart contract to receive Ether and have an Ether balance. We will dive deeper to this later in the course. For the moment, we are going to define our function as payable, which allows people to send Ether to the contract along with the function invocation, and that Ether will be added to the contract balance. So our function bid has been defined as a payable and public function. This means that users can send Ether with the function call, and it can be called externally as well as internally. This function only has one line, which adds a user's bid to the bid's mapping. We grab the user's address with the message.sender keyword. As we've learned from before, the message.sender keyword returns the address of the externally owned account or contract that invoked this function call. We set bids at message.sender equal to message.value. Message.value is the amount of Ether that was sent with message.sender to this function call. Message.value is the amount of Ether in whey that was sent with the function call. Obviously, this auction contract is not fully complete, but you can see how we can store users' bids in our bids mapping. Mappings are very useful, and they are used in almost every single smart contract that you will find. That concludes our lesson on mappings. Structs provide a new way to define new data types. Structs are made up of other data types and are used to represent a single thing that has properties, such as a person, a request, etc. Enums are especially useful to describe the state or flow of a smart contract, or to articulate different stages within the contract. Think of enums as user-defined types that contain human-readable names for a set of constants called members. Enums are explicitly convertible to and from integer types. Let's look at a contract where we use both structs and enums to define various relationships. Notice on line 7 that we've declared a struct called planet. We've declared this outside of the contract, which means that every other contract in this file will have access to this struct. Note that this is completely optional. Unless you're planning on defining more than one contract within a single file, you would normally define the struct within the contract scope. On line 14, we've instantiated our planet. We've created a variable called universePlanet, which is of type planet, and we've given it the public modifier. Next, we've created an enum called state and given it 3 different stages: inhabited, uninhabited, and unknown. Below this, on line 18, we've created another public variable called universeState and given it the type state. You can see structs and enums truly are data types, and when we instantiate variables, we give them the type of the struct or the enum. On line 20, you can see a unique kind of function called the constructor, and as you know, it runs once when the contract is deployed. In our constructor, we're taking in two parameters, _age and _name. You can see that these two fields exist in our planet struct. Within the constructor, we are setting the values of our universe planet struct. We define its age, its name, and its address, which we are setting to message.sender. You can see how we access a struct's value by naming the struct, then using dot notation and adding the field afterwards to get its value. Here we have defined a function called changePlanet. ChangePlanet takes in three parameters, uint age, string memory name, and address. The function is defined as public. First, we have a conditional statement, which checks if the universe state is equal to type of state.inhabited. This is very common for enums to be used this way, to check whether or not certain conditions are met in the contract. In this case, it's determining whether our planet is inhabited or not. But in other cases, you could see this being used for financial applications, such as the status of somebody's loan. If this condition is true, we define a new struct, passing in all of the fields that we accepted as function parameters. Then we set our universe planet in storage to our new planet, which we've defined in memory. Please note the syntax for declaring a new struct. Word by word, we'll break this down. Type planet, stored in memory, called new planet, is equal to a struct of type planet, fields and values, ending with the semicolon. Then we can access our new planet struct, which lives in memory. Thanks for checking out our lesson on structs and enums. We are almost done with the Solidity data types. Before we move on to other core concepts, we are going to look into storage, memory, and call data. These are all modifiers that we can apply to variables to specify where the EVM should store the data. Storage is the most expensive option, but the storage is persisted to the blockchain. Memory is cheaper than storage and offers read and writes, but its data is not persisted outside of the function it lives in. Call data is even cheaper than storage, but it is immutable and read-only. There are scenarios where storage can be more gas efficient than memory, like in scenarios where instead of copying an entire array over to memory, that array already lives in storage. In this case, the storage keyword is better to use because it is cheaper to reference an array that is already in storage than to copy the entire thing into memory. Let's look at our contract. On line 7, we've declared an array of strings called planets. Inside of it, there are two values, Jupiter and Neptune. We've declared a series of functions. Let's look at them in order. Our function fMemory copies the planets array into memory. This will increase the gas cost linearly with the size of the array. You can see on line 12, we declare a new array of strings called S1 in memory, and we're setting this equal to the planets array. This means we will copy the entire planets array into memory on line 12. On line 13, we update the element at index 0 in our S1 array to equal Mars, and then we end the function. Notice that this function will not actually update our planets array. This is because S1 is in memory and is separate from planets, which is in storage. Next, let's look at our function fStorage. First, we instantiate a new array of strings called S1 that lives in storage, and we set it equal to planets. Then we set the element in S1 at index 0 equal to Mars. Then we end our function. This will result in our planets array at index 0 being equal to Mars. This is because when we declare a new variable in storage and set it equal to a variable that already exists in storage, S1 becomes a reference to planets. In this scenario, fStorage will be cheaper than fMemory. This is because fStorage only updates our storage array instead of copying the storage array and then editing it. Let's look at our next function, fCallDataParam. This function takes in an array of strings, esc1, which lives in call data. Call data is read-only, and therefore it is cheaper than memory. We are setting the element at index 0 in our planets array, which lives in storage, equal to element 0 in our S1 call data array. This works because we can indeed read the variables in S1, but we would not be able to say, right, S1 at 0 is equal to Mars, because this is not read-only, this is a write. In our final function, fMemoryParam, we take in an array of strings that lives in memory. This will be slightly more expensive than the same array of strings that we had before, which was in call data, but because it is in memory, it allows us to write to the array as well. You can see on line 31 that we set the element at index 0 to Mars, and then we write to our planets array in storage. So keep in mind that call data is always the cheapest option. However, it does not allow you to write. So if you do need writing capabilities, you should then default to memory. And in cases where the data structure that you'd want to use already exists in storage, you should use the storage keyword instead of copying that data structure into memory. That's a quick intro to storage, call data, and memory. I hope you learned a lot. Let's go on to the next lesson. There are many global variables and functions that exist in the global namespace, most of which are extremely useful and you'll use day to day in your Solidity programming life. In the last lesson, we saw two of these variables, message.sender and message.value. So what is message? Message contains information about the transaction or function call. Message.sender returns the account address that generated the transaction. Message.value returns the ETH value in way sent with the function call. Message.gas returns the remaining gas. Keep in mind that message.gas has been truncated for gas left. Message.data returns the data field from the transaction or call that executed the transaction. Next, we'll look at this keyword. You may be familiar with this if you've worked with classes in other languages. In Solidity, this is the current contract, and it is explicitly convertible to type address. You can use address parentheses this to explicitly convert to the address type. Next, we have block. Block contains information about the block that the transaction is included in. We have block.timestamp, which returns the Unix epoch. Block.number returns the current block number. Block.difficulty, which is the difficulty of a mining block. And block.gasLimit, which is the maximum gas limit all of the transactions inside of a block are allowed to consume. Keep in mind that some of these can be manipulated by miners, such as the timestamp. For example, a miner will be able to manipulate the timestamp by 12 seconds or so, which is around the average time it takes for a block to be mined. So if you're going to add business logic into your contract, be careful when using block.timestamp or block.number, because miners do have control over these ever so slightly. Next, let's look at the TX keyword, or short for transaction. This is similar to message, although it has a few key differences. First, we have transaction.gasPrice, which is the gas price of the current transaction. And next, we have transaction.origin, which may seem very similar to message.sender, however, it is quite different. Transaction.origin is the sender of the transaction, whereas message.sender is the invoker of the current function. So if I call contract A and contract A calls contract B, in contract B, the message.sender will be contract A, but the transaction.origin will be my personal address. Let's look at some more built-in global variables. We have various types of ether units at our disposal. We can add the suffix way, fini, sasbo, or ether to specify a subdenomination of ether after declaring an integer. By default, ether numbers will be assumed to be way. We also have access to time units. Suffixes like seconds, minutes, hours, days, and weeks can be used after literal numbers to specify units of time. Seconds are the base unit. There are a number of built-in global functions which allow us to do ABI encoding and decoding, error handling, math and cryptographic functions, as well as various other built-in global functions. I encourage you to take a second and read the Solidity docs to learn more about these global built-in functions. We've dealt with function modifiers already. You can see here a list of the built-in function modifiers. Let's look at them one by one. Pure and view are both function modifiers. Pure disallows modification or access of state. In other words, pure does not touch anything on the blockchain. It simply returns a value. View disallows modification of state, although it does allow you to view blockchain state. Payable is another function modifier. It allows functions to receive ether with a function call. Constant and immutable are variable modifiers. Constant disallows reassignment of variables. It requires you to initialize the variable with a value and does not allow you to change it afterwards. Constant also does not occupy a storage slot. Constant variables are baked directly into the contract bytecode. Immutable allows exactly one assignment within the constructor function, and then afterwards is stored just like a constant. Use immutable instead of constant when you need to pass in the value at deployment time and you don't know it in advance. Virtual and override are a class of function modifiers. Virtual allows the function or modifier's behavior to be changed in derived contracts. Override states that this function, modifier, or state variable changes the behavior of a function or modifier in a base contract. Let's say you are building a contract based on the erc20.sol contract in the OpenZeppelin library. You may override some functionality in that contract. Therefore, you would give your function the override keyword. Override functions always have the same name and function signature as the function they are. Let's take a look at modifiers in code. We can also write our own modifiers, which you can see on line 7. This is one of the most common modifiers in Solidity, the only owner modifier. What this modifier does is it only allows the owner of the contract to call a specific function. Let's look at the syntax. First, we'll write modifier and then the name of the modifier. We put any logic within curly brackets. We have a require statement that checks to see if message.sender is equal to our owner variable, which we've defined in public state. And then we have this underscore and semicolon. What this means is run the rest of the function. You could also do so like this, where the function body will run and then you check some conditional statement. But in this case, we want to make sure first that the owner is the person calling this function, and then we run the rest of the function. Let's look at a function that implements only owner. We have a function called changeOwner, which is public and uses the only owner modifier. This function allows us to change the owner to message.sender. However, that's kind of dumb because then we can never change the owner. So let's just add an address called new owner and set that equal to owner. Now our function actually does something. So change owner is public and only owner, and it allows us to set a new owner in our contract. So quickly, let's look at how this would work when someone calls the change owner function. So someone would call the change owner function and pass in a new owner address. Our only owner modifier would be triggered. This require statement would run, and then it would run the rest of the body, given that it passes. The rest of the body is on line 25. Then owner is set to new owner and the function ends. So that concludes our lesson on modifiers. Hi, and welcome to our lesson on contract addresses, balances, payable, receive, and fallback. Any contract on its own has a unique address that is generated at deployment. Contract addresses are generated based on the address of the creator and the number of transactions of that account, also known as the nonce. There are two different types of addresses, payable and plain. They have the following members. Address.balance returns the balance of the address in Wei. Address payable has the transfer method, which sends a given amount of Wei to address and reverts on failure. Transfer forwards 2300 gas, and this is not adjustable. Address payables have the send method, which is just like transfer in that it sends a given amount of Wei to an address. However, instead of reverting on failure, it returns false. Send also has the 2300 gas stipend, which is non-adjustable. Address.call is a method which issues a low-level call with the given payload and returns a success condition and return data. Call forwards all available gas, and it is adjustable. Call is actually the preferred method to send ether as opposed to transfer or send. This is because with changes to the EVM, there is no guarantee that the 2300 gas stipend is going to be enough to successfully transfer ether, especially if a contract implements logic in the receive or fallback functions, but we'll look into this later. Delegate call is similar to call, except it provides special permissions to the externally called contract or address. Delegate call deserves its own lesson and is not to be used lightly. Please look into it before using it in your own contracts. And lastly, there is static call, which is similar to delegate call. I encourage you to read the Solidity docs to learn more about these two functions, as they are very complex. A smart contract can receive ETH and have an ETH balance only if there is a payable function defined or a fallback/receive function. Let's get into how a contract can receive ETH in multiple ways. Simply by sending ETH to a contract from an externally owned account. In this case, the contract would need a receive or fallback function. You can also call a payable function in the contract and send ETH with that transaction. Let's look at receive and fallback functions in code. Here we have our contract deposit. Receive functions were defined in Solidity 0.6, and a contract can only have one. It is declared by using the keyword receive, followed by parentheses and external payable. Receive functions must be given the visibility external and payable. The receive function will execute on calls to the contract with no data, such as simple ETH transfers from externally owned accounts or calls made via send or transfer functions. Note that receive cannot have arguments or return anything, and it must have external visibility and the payable modifier. We also define a fallback function beneath it. The fallback function is run when a call is made to this contract, but the function signature does not match any existing function on our contract. Hence why it is called fallback. It runs when there is no other function relevant enough to run. Fallback will also run on ETH transfers with .call, .send, .transfer, except if there is a receive function that will receive priority in terms of .send and .transfers. Note that if we deployed this contract without either of these functions, and somebody tried to send Ether to it, that transaction would revert. You can see on line 26 we have a simple function called getBalance, which is of type view, and it returns the balance of this contract. You can see we use address parentheses this to explicitly convert this to type address, and then access its balance by using the .balance method. In our last lesson, we looked at receiving Ether within our smart contract. Now, let's look at how to send Ether from our smart contracts. We have three functions here: send Ether, transfer Ether, and call Ether, all corresponding to their own method: send, transfer, and call. Our function send Ether takes in an address payable called destination and a uint called amount. This function is public and only owner, which means only the owner can call this function. It returns a Boolean. That is because send returns true or false based on whether or not the transfer was successful. First, we have a require statement, which checks to make sure that our amount is less than or equal to the balance of this contract. We do this to make sure we don't try to send an amount greater than we have access to. Then we put destination, which is the address which we're planning to send the Ether to, .send the amount. This calls the .send function on the address payable destination. This will return a Boolean value, which we've defined as res, and then we return res. Next, let's look at transfer. Transfer Ether takes all the same arguments and has the same modifiers as send Ether. However, it does not return a value. This is because transfer reverts on failure. So we know if the function does not revert, the transfer was successful. We have the same require statement, and then we call .transfer on destination with the given amount. Keep in mind that .transfer and .send both forward 2300 gas, which sometimes is not enough to successfully transfer Ether. Therefore, we suggest using the .call method, which has its own drawbacks. .call is the modern way to send Ether from our smart contract. .call returns two values: a Boolean, determining whether or not the call was successful, and bytes, which contains any return data from our call. We have our require statement, making sure we don't send more than the contract balance. And then we call destination.call. We use curly bracket to determine the value, which we're setting to our amount variable. And then inside of these parentheses, we would put a function signature if we were planning to call a function on another contract. However, we are just sending Ether. In this case, if we were sending it to a contract, we would trigger the fallback function. Or if we send to an externally owned account, just simply send Ether. Then we return our success and return bytes in a tuple. Call is the modern way to send Ether. However, it is somewhat dangerous because it forwards all gas. When we use .call, we could be triggering a fallback function where anyone can put external logic. Someone could write malicious code in their fallback function and attack our smart contract. We don't want that, so there are many different ways to protect our contracts from external contract calls. However, we won't go over that in this course. You will learn more about that later on in the macro pre-course. We will now take a look at variable and function visibilities. There are 4 types of visibilities for functions and 2 for state variables. First, we'll look at public. Public functions and variables are a part of the contract interface and can be called both internally and externally. Public is the default visibility for functions. For state, a getter function is automatically created for public variables. Next, we have external. External functions are also part of the contract interface, but can only be called externally. This means you cannot access external functions from within your own contract. External is not available for state variables. Internal functions are accessible only from the contract they are defined in and any contracts that inherit or otherwise derive from that contract. Internal is the default for state variables. Private functions are only available within the contract they are defined in. They cannot be accessed through inheritance or other derivation. Private is not available for state variables. Let's look at some examples in code. Here we have our contract A. We are defining 2 ints. We have an int public x is equal to 10. Because it is public, it will create a getter function and be on the contract interface that can be called by externally owned accounts and other contracts, etc. Next, we have our integer y is equal to 20. This is set to internal by default and can only be accessed via getter inside of this function or other functions that inherit this contract. Following this, we have 4 functions. We have f1, which is a private view function, f2, which is a public view function, f3, which is internal view, and f4, which is external view. You can see we have one of each type of function. f1 returns y. f2 first calls f1 and then returns the value of that function call. f3 returns x, and f4 returns x times y. Next, we have a contract B, which inherits contract A. Keep in mind, this is how we inherit contracts. We say B is A. This A contract must be in scope, but we can see it's defined here, so we have access to it. If this function is defined elsewhere, we can use an import statement. We've defined on line 31 an integer public called xx and set it equal to the result of f3. f3 returns x, so this is valid. We can call f3 because it is of type internal, and we are inheriting the A contract. Therefore, internal functions are available within the scope of B. On the next line, we have a function that won't work. We try to set a variable called yy equal to f1, but as we know, f1 is a private function, and therefore cannot be called by derived contracts. On line 33, we have another variable called yy, and we're setting it equal to f2. This works since f2 is of type public, and can access the private function f1 because they are in the same contract. Finally, we have another commented out line, because this won't compile, called integer public xy, which is set to the result of f4. This won't compile because our function f4 is external, which means we can't call it within the contract it is defined in or any other inheriting contract. Finally, we have contract C. On line 38 of contract C, we define a new contract. We define that contract as type A. We set it to public, and we call it contract A. Using the new keyword, we can deploy a new instance of contract A, like so. Next, on line 39, we have an integer public xy, which we're setting equal to the result of contract A.f4. From contract C, we can call the f4 function because it is external, and C does not inherit from A. A is a completely separate contract, therefore external methods are available. That was a comprehensive look at function and state visibility modifiers. In this lesson, we'll take a look at events and errors. Events can be triggered by smart contracts, but they are not stored on the blockchain. Events allow for external applications like daemons or front ends to monitor for specific events/actions taken on the blockchain. Event logs provide the contract address, a series of topics, and some arbitrary length binary data. Event parameters can be indexed, but only up to 3 or 4 for anonymous events, which makes them faster to search through. Errors can be customized to return descriptive data to the caller. This descriptive data is the encoding of an error and its arguments, in the same way as data for a function call. Let's take a look at how we can define events and errors in our contract. Here we have our contract, events and errors. On line 7, we define an event called transfer. This event returns 5 values: an address called from, an address called to, a uinteger called value, a boolean called success, and a bytes, which is index, called data. Next, on line 9, we define a custom error called insufficient balance, which has a uint256 called available and a uint256 called required. Let's use both of these in this sendEth function. We have a require statement, which checks to see if the message.value is equal to the value that is passed in. This checks to make sure that the caller sent the correct amount of ETH as they specified in their value parameter. Next, we have a conditional statement, which checks to see if the balance of this contract is less than the value specified. If true, then we will revert with our custom error. We pass in address at this.balance, which you can see is the amount available, and then we pass in the value, which is the amount required. We use the revert keyword followed by the error to pass these values. This will allow for more descriptive error handling on front ends. Following this conditional statement, we perform a .call on the to address, passing in the value. We'll emit a transfer event, passing in all of our fields to describe this event. We describe where the funds came from, who they were sent to, the amount of ether, whether or not it was successful, and any data that was returned with our call method. To emit a function, we use the emit keyword. Again, events are not stored on the blockchain, but you can have software which listens in for these events and acts accordingly. Custom errors and events drastically improve UI/UX of the blockchain and allow for front ends and custom daemon software to listen in for specific events and actions on the blockchain. I highly encourage you, when developing your smart contracts, to keep in mind what events you might want to be listening for. For our final lesson in section 1, we'll look at compilation, ABIs, and bytecode. When we compile our smart contracts, the Solidity source code is passed to the Solidity compiler, and the compiler returns the EVM bytecode that is deployed and the contract ABI, which stands for Abstract Binary Interface. The ABI gives instructions to other applications as to how to communicate with our smart contract. Contract bytecode is public. It is saved on the blockchain and can't be encrypted because it must be run by every Ethereum node. Opcodes are the human-readable instructions of the program. Opcodes can be easily obtained from the bytecode. However, the contract source code does not have to be public. There is no way to get Solidity source code from the bytecode alone, but most contracts are published to build trust and support transparency on the blockchain. As you can imagine, it only improves the community if everyone can read the source code behind the smart contracts they are interacting with. In our hardhat environment, we can compile our contracts by running npx hardhat compile. After our contracts are compiled successfully, hardhat will generate two folders, cache and artifacts. If we go into our artifacts folder and we go into our contracts, let's find the ABI, which was generated when we compiled the code. In our artifact folder, we can navigate into our most recent lesson, which was events and errors. This is our JSON file, which has information about our contract. Here you can see a field that has our ABI. Our ABI is an array in JSON with all of our different methods and types. I've highlighted it here. In our contract, you can see that we only have one public method called sendETH. Let's find that in our contract ABI. You can see that there's a method called sendETH. It outputs nothing. It has a state mutability of payable, and it is a type function. Look at that. Underneath the ABI, you can see the contract bytecode. It is very long. Let me wrap it just so we can take a look. This is the contract bytecode, and this is the deployed contract bytecode. This is public information. The ABI, not so much. But again, most contracts are shared publicly, which allows people to generate the ABI on their own. That was a quick look at compilation, ABIs, and bytecode. Hi, and welcome to the Lottery Smart Contract project. By now, you should have already forked our course's GitHub repository. If not, I'll link it in the project resources in Udemy. Let's head over there now. In the README, under the Lottery Contract section, you will find instructions for the project. Let's read over the spec together. The lottery contract is a smart contract where people can enter the lottery by sending 0.1 ETH to the contract. When the owner of the contract decides, they can call the function pickWinner, which will select a random player and award them with all of the ETH from the lottery. Let's look at a more technical spec for the contract. Anyone is able to send a fixed amount of Ether to the contract's address. The address of the sender will be stored in a dynamic array called players. The same user can send more than one transaction to have more chances of winning the lottery. The same principle as in a classical lottery, where you can buy as many tickets as you want at a fixed price per ticket. The contract has an owner with special permission. After there are at least 3 players, the owner can call a function that makes the contract pick a random player from the list, which will be the winner. The contract transfers the entire balance to the winner's address. The players array is reset, and then the lottery is ready to play again. The lottery.sol contract is full of comments with to-do tasks. Please complete all of the to-dos listed in the comments in the lottery contract, and then run npx hardhat test to check your work. There is a solution lecture at the end of section 2 on Udemy, which explains the contract line by line. Let's take a look at the lottery.sol contract. You can see there are various to-dos throughout the contract, like this one on line 14. Initialize the owner to the address that deploys the contract, and more. Please go through these line by line, completing the contract as described. When you are done, run npx hardhat test to check your work. I'll see you in the solution lecture. Hi, and welcome to the solution lecture for the Lottery Smart Contract project. I'm going to go over each answer and each to-do in the smart contract, line by line. Let's look at the to-do where we initialize the owner to the address that deploys the contract. We'll hop into our constructor function because we know that the constructor runs once on contract deployment. And we set our public variable owner equal to message.sender, which we know is the address of the contract or account who called this function. And since it's the constructor, that will equal the deployer of the contract. Next, let's go into our receive function. We want to make sure that each player sends exactly 0.1 ether. We can do so by adding a require statement, which checks if the message.value is equal to 0.1 ether. Message.value is the amount of ether that was sent with this function call, and we can use the ether suffix to quickly turn an integer into a denomination of ether. In our case, 0.1 ether is exactly the amount that we want. Next, we are going to append the player who just entered the lottery into the players array. We can do this by calling the .push method on our players array, which lives in storage, and passing in message.sender. Of course, message.sender is the person who's entering the lottery, as they sent ether to the contract. That is all we need to do for our receive function. Let's write a function that returns the contract balance in way. We want to restrict this function to only be called by the owner. So let's add a require statement, which checks to make sure that message.sender is equal to owner. And we can pass in this error message string, only owner, to give clear error messaging. Then we can return address at this.balance, which is how we access the balance of the contract. Finally, we'll enter our pick winner function, which is the function that will end up selecting the winner of the lottery. First, we want to make sure that only the owner can call this function. So we add our require statement just like before, where we check message.sender is equal to owner. Note that you can create a modifier function which checks to make sure that message.sender is equal to owner and add it to both pick winner and get balance. Next, let's make sure the owner can only call the pick winner function successfully if there are at least 3 players in our lottery. We can call the length member on our players array, which returns the length of the array. Then we can perform a conditional check which checks to make sure that players.length is greater than or equal to 3. Otherwise, we will return the error not enough players. Next, we'll call the random function and assign it to our uinteger r. Keep in mind that the random function is not safe to use because it is not truly random. The numbers that we are using do create a pseudo-random number, but this can be recalculated on-chain and exploited by malicious users. Please read into the Solidity by example randomness article to read more about randomness. Just know that if you want a truly random number, you would have to use something like Chainlink VRF or some other external oracle which provides verified random numbers. Then we declare a local variable which is of type address called winner. Next, we will take our random number and turn it into a random index in our array. By taking our random number modulo the length of the array, it will return a pseudo-random number which is going to select a winner in the array. Using the modulo, it won't allow us to pick a random number which is outside of the bounds of our array. Therefore, we can set our winner equal to players at index, which is the random number we just calculated. Then we push our winner into our game winners array. Then we will reset the lottery for the next round by calling delete players, which will delete the players array. Calling delete players will remove all of the elements from the array and reset the length of the array to 0. Next, we will transfer the entire contract balance to the winner. We will use the .call method on our winner's address and pass in a value of our getBalance function, which we know returns the value of this contract. Finally, we will require that the return value of our call is successful. Otherwise, we will revert the transaction. That was our solution lecture for the lottery contract. I hope you enjoyed the course.